Hello, everyone. We're about to start. Welcome to STG329. My name is Andrei Zaychikov. I'm a solution architect based out of Luxembourg. I'm working for AWS. And today we're going to talk about how ProtectWise optimize performance of Cassandra and Kafka workloads on Amazon EBS. I would like to ask you to welcome my co-presenters, ProtectWise team, Gene Stevens, who is CTO and co-founder of ProtectWise, and Robert Terrell, who is Director of DevOps in ProtectWise. Today we're going to have a pretty busy agenda. We're going to have an intro to NoSQL on AWS. We're going to discuss how Cassandra and Kafka work. We're going to cover some best practices for these types of workloads on AWS. And of course, we're going to go through ProtectWise use case and their use case for Kafka, Cassandra, S3, and some specific optimizations they made on AWS. And of course, we're going to have some lessons learned. I would like to start with this slide, and would like to start with NoSQL as a technology. We often refer to NoSQL as a technology, but it's not really something like that. It's more like a movement and a bunch of technologies combined by the similar ideas. It started quite some time ago, and most of the protocols were well known actually in 90s and 80s of last century, like Gossip Protocol and Paxos and so on. But the big movement started in 2004 with a MapReduce paper, which wasn't directly referring to NoSQL, but that made a great shift. And in 2007, Dynamo paper was published, and that was published by Amazon, and that was a huge step forward, NoSQL databases and NoSQL world. And in 2007, a lot of different projects started, like MongoDB and Neo4j, and in 2008, Apache Cassandra started, and we're going to talk about Apache Cassandra today. And since 2012, we have a lot of new databases coming in every year, solving different aspects of NoSQL workloads and different aspects of data processing. Nowadays, how to pick up the database, the best thing is to go for database per workload approach. So for example, if you have something like caching, you need to know your workload for sure, right? But if you have something like caching or something like data streaming, for data streaming, for example, you can go with Kafka or other options, right? For caching, it's either Redis or Memcache. So you can have key value in memory databases for fast data processing. You can have, of course, relational databases, which will be nice for the workloads which need really high consistency of data, and it can be like MySQL, Postgres, or some other choices, right? Of course, you can have like search engines like Elasticsearch, Solr, which really nice play for like different types of variable requests. You can have graph databases, and of course you can have something like a big geo-distributed database like MongoDB and Cassandra, which can be like a main source of truth and main database for high throughput, both for reads and for writes. If you can see, like, as you can see, there's a bunch of different databases, and if you can imagine the huge clusters of both like Cassandra and Elasticsearch and Solr and Redis and so on, it's kind of really complicated to manage that, right? So we have a bunch of options for databases on AWS, like Amazon Elastic Cache, right? Like DynamoDB. Like Kinesis for streaming, Amazon Redshift as a data warehouse, and Amazon Elasticsearch as a managed service engine, so which plays really cool. But today we're going to talk about DIY kind of setups, Cassandra, Kafka on AWS. And for these, the essential part, of course, is storage. And we have like several major services for storage, like Amazon EBS, we're going to talk about that today, Amazon Elastic File System, S3, of course, Glacier, and so on. And what is nice about these services that they are completely managed by AWS, and they are really tightly integrated with different management tools, with security tools, and you don't need to bother for integration or maintain these types of integrations and so on. So what's Cassandra and why to use that? Apache Cassandra is an open source database based on Dynamo model. It's massively scalable, a geo-distributed, high-performance key-value database. So it can scale up to 1,000 nodes really quickly and quite fast and efficient. Among most often use cases for Apache Cassandra, like time series data, data for social media platforms, and like e-commerce data, like user sessions for e-commerce and so on. So how Cassandra works on the cluster level. You can see the green box. It's a cluster. It's a Cassandra cluster, which is the main deployment unit in Cassandra. Inside the cluster, you can have multiple, like blue boxes, multiple data centers. And data centers are there for geo-distribution. And inside the data center, you can have racks. And racks are there for disaster recovery and high availability. So inside the racks, you can have, in the cluster, you can have one or many data centers, and inside the data center, you can have one or many racks. Inside the cluster, there are nodes. And Cassandra is a hash ring, so basically, it doesn't have any single node of failure, or it's masterless, right? So any node can act as a coordinator node and can coordinate the requests to all the other nodes. And on the cluster level, what you can have is of course, it's snitching. So it's a concept of node discovery and working with different types of nodes. And there are some snitches for AWS specific, like EC2 snitch, multi-regional EC2 snitch. There is network topology. There is read and write consistency on the cluster level. And the nodes are interacting with each other with the use of gossip protocol, and they're actually gossiping it around the state of the cluster and where the data resides on the nodes. So how Cassandra works on the node level. This diagram shows both reads and writes for the node. So solid lines are for reads and dashed lines are for writes. So what we can see here, like a write is quite straightforward. Cassandra node starts to write in a commit log first, which is there for disaster recovery mainly. And after that, it writes to mem table. And after it is written, the data is written both in commit log and in mem table, the write is successful. After a certain amount of time, mem table is flashed on the disk, and it effectively becomes SS table, which is a mutable structure which cannot be changed. So the data is immutable there. It can be the data, the SS table can be deleted during the compaction process, or it can be recompacted and stuff like that, but neither can be changed. In addition to these two things, during the write process, you can have a hinted handoff. So if no nodes are available for the write of the particular key, the coordinator node can store it in the hinted handoff, and the write will be delayed. So the read sequence is a bit more complicated. The thing is, like, the data is immutable in SS tables, and you have per node, you can have like hundreds of SS tables, and they can be quite big, right? So they can be gigabytes of data per SS table. So to manage, to be able actually to read this data really fast, the first thing which is implemented in Cassandra is a Blom filter. Blom filter is a probabilistic structure which answers quite a simple question. Is there any chances that this certain key is within this SS table? So yes, if it says no, so it means that 99% that the data shouldn't be in this SS table, and it goes to the next SS table. So after Blom filter is checked, then it goes, the Cassandra node goes to key cache if it's enabled, and by default it's enabled, and tries to find where's this key on the disk on the particular SS table. Then it goes to the partition summary and tries to find where is the position of the particular key in the partition index to find the position of data and read it. One more thing, as SS tables are immutable, there are certain procedures called compaction procedures which are implemented on the node level. So they can be like four main types of compaction: size-tied compaction, which is a default type of compaction, and which is really suitable and well suited for write-heavy workloads. Then it can be leveled compaction, which fits more like 80% read pattern. And you can have time windowed compaction or data-based compaction, I mean, based on the particular time or date. So you can have SS table for Wednesday, for Thursday, and so on and so forth. So how application interacts with Cassandra? Application interacts with Cassandra with the use of driver normally. And drivers have a bunch of settings actually. One of the most important thing is the load balancing, and you do a lot of cool features there. So for example, you can whitelist a set of nodes inside the Cassandra cluster and only work with these nodes. Another feature, you can have like a round-robin load balancing policies and so on. In addition, what driver does, it helps you to deal with errors, to handle errors. It has a retries policy, so again, to deal with errors, you can just retry the request. And of course, you have to think about like consistency level, both for reads and writes. By default, it's local quorum, so which means if you have replication factor free for Cassandra, if two nodes return the same result, the read will be successful. Some best practices for Cassandra on AWS, there are a couple of those. First thing is like from infrastructure standpoint, think about cost of traffic, because traffic has cost, and for the big clusters like thousands of nodes, the cost can be quite high. So next thing from the operations side, regular repairs, it's really important for Cassandra. And you can utilize EBS features like EBS snapshots for backing up your data, for bringing the node really fast online. And for planning scaling operations, you can use EBS elastic volumes feature just to have a really fast increase of IOPS on the GP2 volumes. So from application data schema, the most important thing is like to carefully pick up the partition key to avoid hot partitions and so on. And just consider some like collecting the data from errors on the application side, because it's a big part of the picture what's going on with your Cassandra cluster. So what's Apache Kafka and why to use that? Apache Kafka is an open source distributed streaming platform, and it allows you to publish and subscribe to streams of records, stores these streams in a fault-tolerant way, process them. And most common use cases are like either to build the data pipelines to capture data and transfer data between systems and applications, like a queue style, right? Or to build the real-time applications which actually react to the streams of data. So Kafka is often put before the actual database to remove some of the load and to reduce the amount of load put on the database. So how Kafka works, there are two major things on Kafka. The first thing is logical unit, which is called topic. So basically your application works with topic. And topic can be divided into multiple partitions. And partitions are replicated across the nodes in the primary, secondary mode. And the partitions actually consist of segments, and effectively each segment is a set of two files. It's index file and log file. In addition, you can have two types of applications working with Kafka. One is producer, which actually writes the data, and another one is consumer, and consumers can be combined in the groups to be able to read the data efficiently. So, and Kafka relies on Zookeeper for monitoring, for keeping the cluster state, keeping the node state, and so on. Some best practices around deploying Kafka on AWS. Of course, the first thing is to isolate Kafka data on a separate disk, because it takes some time for Kafka node to be online after it joins the cluster. So for each node, it's better to increase max number of file descriptors per process, because it's really crucial. Kafka works with an enormous amount of small files. Then on DB settings part, it's general best practice to over-provision the number of partitions, and the guys from ProtectWise will explain you why. And of course, you have to configure correctly Zookeeper and to be able to fail over and to the other nodes, right? So choosing proper instance and storage types. Of course, everything here, it's really crucial and important topic, and everything here depends on database implementation. I mean, the particular database like Cassandra, Kafka, and so on your data schema, on access patterns. It's something always to consider. And of course, you can adapt the compute and storage types on the go. So if your demand change, if your pattern change, you can adapt that. So for Cassandra workloads, we have the benchmark here, which has two axes. The first axis is a request per second, and the second one is volume. So if you will see on the, if you will look at these diagrams, if you have like a general workload with like any amount of data and not really high RPS, you can go with IM4s and GP2s as the volumes. If you're, and after that, if you're like really need a high throughput on the database and your amount of data is quite relatively small, what you can do, you can go either with I3s or I2s, both for reads and writes cases. But if you have, for example, 50-50 read and write ratio or like more write-heavy workload, you can go with a C4s because Cassandra is CPU bounded, and you can use GP2s. As well, it's a good practice to use ST1 EBS volume for the commit log. It's quite cheap and it has a really high throughput. For Kafka, general recommendation, like for most of use cases, is to go with R4s and to use ST1 EBS volume, which is recommendation given by Confluence, or depending on the case, if you have really a lot of small files, the best thing is to go with GP2s. So I will hand it over to Gene, and he will go through ProtectWise use case. Please welcome Gene.
Thank you, Andre. As he mentioned, I am Gene Stevens. I'm the co-founder as well as the CTO of ProtectWise. And what I'm going to do today is talk you through our use case. I'll be followed here very shortly by one of my colleagues, Robert Terrell, who's the director of DevOps. He's actually responsible for making sure this stuff functions well in production. But let's talk you through our use case a little bit. Here's a basic, really basic architectural overview. ProtectWise is a cybersecurity company. We actually have a data platform running inside of AWS, and that it consumes a tremendous amount of data. It has a lot of data in motion, a lot of data at rest, and it really uses this data in a very aggressive manner in order to detect threats and attacks, these types of things. So I'm not going to tell you a lot about the business, because I'm not supposed to, but also because I want to focus on exactly some of the technology challenges we have here. So I'm going to talk you through a little bit about how data moves through our platform and how we kind of think about some of these problem spaces. What I'm about to describe to you actually is going to sound really like overly ambitious to the point of foolishness. And in fact, it was a really great experience for us when we were getting this company off the ground 4.5 years ago, where we were out in the valley pitching, raising money, and doing that kind of thing. And we described what we wanted to do, what you're seeing drawn up here, to a lot of people out there, and they're like, that is nuts. The state of technology is not equal to this problem domain. So let me step into this, because a really big takeaway for us was not just the motivation to say, oh, wow, if we solve that, it's going to be awesome then, right? But to really kind of relay this idea that really big problems, super hyper-aggressive workloads and demands, there's this whole back catalog of technology things we know that we want to do, and we kind of long to live in some future state where that stuff is easy and normal. And we probably want to have this case study have the effect of saying maybe there's things in your workloads that you're looking at that look like that'd be an absurd luxury that are actually pretty manageable. So let's step into this a little bit. Like I mentioned, ProtectWise is a cybersecurity company where we basically deliver our enterprise security from the cloud. And what we do is we actually memorize at the packet level the communications happening inside of our customers' networks. And we're going to ship that to the cloud and create that as the pressure and as a transaction workload that we're going to walk you through some of the architecture of how we address it, how we get that to scale up. So inside of our customer's network, and I think I got a laser pointer here. I'm not sure if it works. It does not. Okay. On the right-hand side, you can see we have a list of blocks by our customer network. We have a lightweight software sensor that we give our customers, and it's typically attached to like a span or a tap. Sometimes it's inside a data center, it's in the cloud, it's industrial assets. We don't really care, which means we're not the boss of what kind of data we end up seeing, which is a really interesting problem. So they're attached there, they're doing packet capture, and just for the conversations that we're going to have today, let's just assume that this works, right? They actually take that data, they compress, optimize, and stream that, often over the internet, though sometimes over dark fiber, to AWS. And that is being ingested at line rate. So this is a near real-time system. Something's happening locally on the network pressure, network transactions, bits and bytes, the ones and zeros that go across the wires, go across the Wi-Fi, et cetera, are being captured and being relayed in a really compressed and efficient binary format to our cloud, where we ingest this at line rate. So we sell the service, and we measure it in like gigabits per second, megabits per second, depending on the size of the customer. And we just kind of absorb whatever they throw at us. That's in the aggregate. That can spike wildly, 10x, 100 times. It's a standard workloads, and we're just going to absorb it. So it's going to hit our ingest service, which you can see here on the left side of those vertical dotted lines, that blue box. That ingest service gets that line rate data. We have packet data, we've got metadata that we can extract from packets coming in. We also have context and other information from like the endpoints and the firewalls and that kind of stuff coming into our platform. In some cases, the metadata about the network traffic is actually a greater amount of data than the actual traffic itself. It's a really interesting problem. As it gets ingested, we push it through this process of line rate destructuring the data. It's kind of like a beam of light hitting a prism, and it kind of bands out into many different colors, right? Well, we have many different forms of data being spread into our platform, but there's two really general tracks here we're going to talk about. There is a track of data that is about the packets that we receive, and it looks like we misspelled it here, that is being stored inside of S3. And then we have the metadata that we actually extract, which can be really voluminous, and that's being passed into Cassandra and Solar. We're going to talk a bit more about that today. I want to be clear for today, Cassandra and Solar for us is DataStax Enterprise. And that is being stored in EC2, EBS, but also inside of what we call our cold store, which is in S3. And we're going to talk to you a little bit about how we built a system that can query data in S3 and get like 1 to 3 second response times, even while scanning, quote unquote, hundreds of billions of rows at a time. So the system is meant to scale really well. We peak over 10 million transactions a second. It's probably closer to 15. It's changed since we put up the slide. We do about 100 billion transactions a day, and we have many petabytes at rest. And we're going to describe a system that streams data, coordinates in a fully distributed manner, handles all of that, and stores and indexes it. We have indexes in the petabyte range. I mean, this is a really big set of data. Okay, some screen candy. The short of it is that we're not just going to absorb this data in order to allow us to kind of use it offline or asynchronously. We're actually going to give our customers direct access to this. We're going to have a system that's going to process and move this data with the expectation of real time. Something happens locally on their network latency later, it's available for human interaction and human inquiry. Asking questions about it. The things our customers do will be investigate attacks, identify threats, remediate, et cetera. And so a lot of actionable intelligence that has really strict real-time requirements or near real-time requirements. And so by presenting this together, we have this large multi-tenant system that we can sell to our customers that has all this data in the aggregate and all the multi-tenancy challenges inside of one single memory for the network in the cloud, and that transitions into something that people use to detect attacks in real time. But we're also going to store an unlimited amount of copy of this data. Our standard offering actually is a year of retention, which is just nuts. And we're going to let people search it and say, we want those search times to return in 1 to 3 seconds. So really high-level goals. I'm going to hand this off to Robert, our Director of DevOps, and he's going to talk you through some of the audaciousness of this, which I hope is super encouraging because it's super fun, but also to talk about there's really practical ways to step into a ludicrous amount of data, have it perform really well, and be really cost-effective. We are a venture-backed startup. We had to solve this without bankrupting the company or running out of money, and so we found a way, and we're going to show it to you guys.
Thanks, Gene. So this is kind of in a nutshell what we were trying to build. Like, this is the shape of the problem we're trying to solve, is to have a data pipeline with very low latency. We wanted to detect threats quickly. It needed to be high availability. We don't really have any tolerance for downtime or data loss. The database needs to handle billions of writes per hour, trillions of records per year, be able to handle those 100x bursts that Gene talked about, and still be able to do searches with kind of sub 10-second response time, even for really arbitrary queries. I mean, being able to search for just like, I want to see this IP for this time range is pretty easy, but if you want to say, hey, for the finance department for the last week, do we see any traffic that was on port 80 but was not HTTP protocol? From a threat perspective, that's really interesting. That could be somebody trying to egress data, or a threat coming in, trying to get through the firewall without being noticed. And that's classically a really hard problem for a typical database to solve. So first I want to talk about how we achieve the low end-to-end latency and the high burst tolerance, so the data processing pipeline, basically. So this was our initial architecture. When we started, we figured, all right, we ingest the data in an intake, we run it through each processing engine in turn. Once it's gone through all the processing engines, and they publish their results to Kafka, we'll store the data into S3 once we're done processing it. The major problem we had here is that these engines, some of them, may not be burst tolerant. They may have problems dealing with a particular class of data or something like that. And, if we've got all the way over on the right, if engine 3 is a little bit slow temporarily, that backs up all the way back up to the customer sensor. And the customer doesn't have this, ludicrously large buffer that we potentially have with S3. So basically what we did to solve this was, instead of doing that, we write the packet data immediately on reception. We write the packet data to S3. And then we're publishing just references to the S3 objects in Kafka. So if you're a programmer, this is kind of like saying, pass by reference instead of pass by value. The data that's in Kafka, we considered trying to pass all of this through Kafka, like all that packet data through Kafka and using it that way, but the size of the Kafka cluster we'd need to run would be pretty crazy. So that wasn't really an option. So this is, the pass by reference thing really saved us here. And then what happens is, from there, the data is each engine runs essentially the same consumer group, consumes the same topics from Kafka, figures out which data it needs to process, downloads it back from S3, processes it, publishes the results to Kafka, and then those results are persisted to Cassandra. So we're sort of using S3 as a queue here. It's doing the heavy lifting for us. Kafka is handling the message semantics, that at least once guarantee and that sort of thing. But S3 is handling the big data volume. So to talk a little bit more detail about our Kafka clusters. Today we have about 45 Kafka brokers, about 1,000 topics, maybe 1,200 partitions per broker. We used to have a lot more topics than that. We used to go with a topic per data type, per sensor, per customer. The problem with that is that ultimately a topic is kind of a unit of scaling. Like if you have 12 partitions in a topic, then you can have 12 consumers on a topic. And so if you get one burst from one customer, they're kind of saturating their own little topic. If we share a topic, then we have more economy of scale. We're using GP2 EBS volumes, as Andre mentioned. ST1 is a much more typical use case for Kafka, but because we're publishing very small messages and because we have a lot of partitions per broker, we're concerned about the amount of random I/O we do, and so we use GP2. And yeah, as you can see, we peak over 100 megabytes per second per broker today, with no problem. So we initially went with Kafka because we needed a message bus that we could scale, would ensure we didn't drop data. It has an at least once guarantee, and that's really crucial for us. We're more concerned, if we reconsume the same data by mistake, that's not a problem, but if we fail to consume data, if we fail to detect a threat, that would be a big problem. But something we didn't really think about when we chose Kafka that has been a huge win for us has been testing in production. You guys probably seen the t-shirt, I don't always test, but when I do, it's in production. We actually do a lot of testing in production. Part of that is because of our scale. It's really hard to afford to run a whole second like copy of production that's at this kind of ludicrous scale, and have customers not paying for it. But it's security sensitive data. We don't really want to take a copy of the customer's data and just copy it over into our test environment that's potentially less secure. So what we can do instead is, if we have a new version of an engine that's got significant changes, we're not sure how it's going to perform, or we just want to make sure that it's bug-free, we can have it consume from the same topic that the current production version is consuming, have it published to a profiling topic, and then compare the results and make sure that it's still working okay. Likewise, we can test significant changes to make sure that they'll keep up performance-wise, make sure that it's not falling behind if we change GC settings or instance types or whatever. So some notes about Kafka. A Kafka partition is your fundamental unit of scaling. So use lots of partitions. I mean, not millions or something, but we kind of try and target about 4x to 10x partitions per consumer so that we can add more consumers. Obviously you can add more partitions to a topic, but if the data is already in there, the new partitions that you add are going to be empty. You want to keep an eye on so I think earlier I may have said 200 partitions in a topic in some of our larger topics. It's actually 192 is the number we use right now. We tend to use multiples of 6 or 12 kind of thing. So with 192, you can have 12 or 16 or 24 or 96 consumers, and everybody's getting an equal number of partitions assigned to them, so you get even distribution. Something to consider is the partition assignment strategy. The default partition assignment strategy in Kafka is still the range assignment. If you have consumers that are reading multiple topics, like one engine, for instance, in our model, that's consuming several topics, the round robin partition assignment is what you want rather than range, just for scaling reasons. The range partition assignment says for each topic that you're consuming in this consumer group, consumer number 1 gets partition number 1, consumer number 2 gets partition number 2, et cetera. So if you have several topics and each have 10 partitions, you can do 2 consumers, or you can do 5 consumers, you can do 10 consumers. But if you add an 11th consumer, he's going to be bored. If you have 9, that first consumer is going to get partition number 1 and partition number 10. He's going to get double the workload. That's obviously not ideal. So with round robin, what it does is it takes all the partitions of all the topics that are being consumed by the consumer group, shuffles them, and then assigns them kind of, in round robin order. And what that means is if you have, let's say you have 10 topics and 10 partitions, that's 100 total partition topics. If you got 20 consumers, each one's going to get 5 partitions. So it allows you to scale better. Some caveats and warnings about Kafka. Now, something that we recognized recently that we hadn't really budgeted for or considered was the cross-AZ replication cost in a large Kafka cluster. Kafka only has limited rack awareness. You can make sure that the second copy of your data is not in the same AZ as the first copy of your data. So, if we lose an AZ, the Kafka cluster can keep on trucking, which is great. But producers and consumers only talk to the leader of the partition, wherever that is, that's who they're talking to. The upshot of this is with replication factor 2. So if you have your primary copy of your data and then one backup, your data could cross AZs 3 or more times, 3 times just with a single consumer or a single producer. So here's how that looks. So you've got a producer producing data. He writes it to the leader. Now the leader's got to replicate the data. So the write already crossed the AZ once. Now the leader replicates the data back into the first AZ again. So it's crossed the AZ boundary twice. You've paid network traffic twice. And now the consumer reads the data, and he's crossing the AZ boundary again. If you have many consumers of the same data, that multiplies. Here's how that looks in perspective. For those 45 nodes, $8,000 for the reserved instance pricing on those nodes. I think they're C4 2XL. And then another $8,000 for the GP2 EBS volumes. That would be half that. If we used ST1, it'd be $4,000. But it's dominated by the network traffic. It was over $40,000. Something else to keep in mind is that a single broker failure impacts the whole cluster. Now, if you lose a single broker, it's not that the cluster's down forever until the broker comes back up. But what happens is when the broker fails, any partitions that he was the leader for, there needs to be a leader election held to figure out who now is going to own that partition. On large clusters, that can take over a minute. And then if that was a broker restart, like a crash or something like that, for us, it always seems to happen that the broker returns just as that rebalancing has finished up. So while that rebalance was going on, the producers were paused, the consumers were paused, rebalance is done, they're just starting to get ready to consume data again, the broker comes back, leader election happens again. So plan for occasional pauses. Like it's normally working fine, but if you can't tolerate the occasional minute or two of stall, this may not be ideal for you. Something else is mostly trust the default settings with Kafka. We've gotten into trouble a few times tweaking settings. It's pretty much all of the settings, particularly the timeouts, seem to be law of unintended consequences. You know, you get like, we increase the timeout to get fewer rebalances, and we get fewer rebalances, but the flip side is that the cluster takes longer to notice the consumer died, and meanwhile everybody else is still consuming, and then it figures out that the consumer died, and so it says, all right, we got to rebalance this, and everybody consumes the same data over again. So aside from partition assignment, where round robin I think is significantly preferable, spend some quality time with the docs before you adjust the defaults. All right, so that was how we're using S3 as a queue. Now I want to talk about how we're using S3 as a database, and particularly how we got there. So this is the shape of what we were trying to build. Needed very high throughput, good burst tolerance, high scalability. These are all Cassandra's sweet spot. But we also wanted to support those arbitrary queries, and that's definitely not Cassandra's sweet spot. You pretty much, you're only doing either primary key lookups in Cassandra or using a secondary index for a specific thing, but if you need to do just every single column is indexed effectively, that's not Cassandra, that's Lucene. So either Elasticsearch or Solar Cloud, or for us, because we were already using DataStax Enterprise, they have a product that is called the DSE Search that just basically, Solar is tightly coupled to Cassandra, which is nice because if you're using Elasticsearch or Solar Cloud, plus a database, you write to the database, then you write to Elasticsearch, and you hope that both of those writes succeeded. And as you may know, Elasticsearch has had consistency issues over the years, so typically what you end up doing is having some batch job that later goes back and makes sure that all the data you wrote to your primary database really is in your index. We haven't had that problem with DataStax Enterprise, so that's been fantastic. Normally, you'd like your Lucene indexes to live in memory, whether it's DataStax Enterprise or anything else. But the volume of data that we were dealing with, that was clearly, that wasn't even vaguely acceptable to be buying many terabytes of RAM, and trying to keep it all in memory. So we initially stored it on SSDs, i2-2XLs, and that was just barely fast enough. It took a ton of tuning, but we got there. The problem is that a month of data, roughly speaking, was about 100 i2-2XLs, and we keep a year of data. So the first month is fine. 100 i2-2XLs is pretty expensive, but okay, we've got some big customers, we could deal with this. But by the end of 12 months, we would have 1,200 of those. That wasn't so good. I should also mention we sharded by time. We did that mostly because it's very difficult to scale DSE search because you have to re-index, like the data that is streamed to a new node, if you expand the cluster, has to be re-indexed in Solar. But we got some huge wins out of sharding by time, and I recommend to everybody that's looking at any NoSQL, this is not a Cassandra thing or a Kafka thing or anything. If you're looking at a NoSQL product and you're hearing these talks about we're running 1,000 node cluster of something, I guarantee you there's an ops guy up at night like not sleeping well about that 1,000 node cluster. And if you can make it 10, 100 node clusters, it's a lot easier to deal with. So in our quest to reduce the price, we realized that our data, once we had retired a shard, essentially, once we'd rolled a new shard and the old shard was no longer taking primary writes, it was still taking a few writes, but the write volume was much, much lower. And at that point, we were actually able to store the data on GP2 EBS volumes on R4 2XLs. And that was, I think, about a 50% cost savings, 50 or 75% cost savings. Unfortunately, migrating the data off the I2s to the R4 2XLs was very operationally intensive. We could do it and it saved us the money, but it was a ton of manual labor. So lessons learned at this point. If you go this route with this kind of data set, expect to spend a lot of time on tuning. There's a lot of outdated advice out there. Talk to DataStax if you're using DSE. They have some tuning advice that was battle tested at ProtectWise. They came out, spent a few days with us, went back with like 20 JIRA tickets that are all resolved now. So, but some of the outdated advice out there you'll see is like, you should never have more than an 8 gig heap size for Cassandra. Well, for DSE search, you really want more like 30 gigabytes, and G1GC works very well for that. I've also seen some FUD about G1GC. We haven't had any issues with it, so I definitely recommend it for high heaps. And if at all possible, use Amazon EBS rather than ephemeral. The operational, I'll get into this a little bit more later, but the operational gains that you get, if you can possibly use it, are definitely make it worthwhile. Actually, here, talk right now about why we want to use EBS. So the first thing we noticed was that instances without ephemeral attached seem to fail less frequently, like noticeably less frequently. I would assume, I haven't asked Amazon this, but I would assume that disk is one of the things that fails. If you don't have disk attached to it, then it's one less thing to fail. I assume that that's why. EBS volumes do fail, but it's really, really rare. Obviously plan for it, but in the last 4 years, and we currently have about 4,000 EBS volumes, I think, in US West 2. In the last 4 years, I think we've had 3 EBS volume failures. So it happens, but obviously we've had that many instance failures in a week. So it's much more rare. And losing the data, having to restore the data from backup or having to stream it back from a replica is the much more intensive issue. If you get an instance failure with nothing but EBS involved, you just stop the instance and start the instance, and you're on new hardware and your data's still there. More importantly for us were the gains that we got from decoupling state from compute. This is something we weren't aiming at when we went into it, but this was a big lesson for us. The whole stateless web app thing, like the web guys figured this out years ago that stateless is fantastic. But we've always assumed, well, it's the database. You can't, that's where the state is. You can't be stateless there. But if you have the storage decoupled from the compute, one of the things that means is if you've got a Cassandra cluster that needs more CPU, you stop one AZ, change the instance type, start it back up again, stop the next AZ, change the instance type. Now you have more CPU, more memory, whatever it was you needed. We did this as we were streaming data over so that we could re-index data more quickly. Likewise, if you run, you get a customer that just suddenly starts shipping you massive amounts of data and you're suddenly about to run out of disk space, you can expand an EBS volume where with ephemeral store, you can't just say, hey, I like my i2 2XL to now have 3 terabytes. All right, so despite all the wins that we got from EBS, we needed something less expensive. Even that 50% or whatever it was cost savings was not enough for the data set size that we had and the size company that we are. So wanted to get off ephemeral entirely, and we wanted to stop running a dozen huge Cassandra clusters, even if they're on EBS. So we figured, hey, S3 is cheap. How can we use that? It's working pretty well as a Kafka queue for us. So what we ended up doing, and this is basically the right path for the data arriving in our system, or really the metadata arriving in our system, is we're initially writing it still to Cassandra and indexing it Solr. But after a few hours go by, when most of the writes have finished, and by that I mean we still have observations that come in maybe weeks or months later where we find out, hey, there was a threat here that we just discovered. But the vast majority of the writes have completed. So after a few hours, we can pull the data out of Cassandra, run a Spark job to create Parquet files, write those Parquet files to S3. While we're doing that, we're also computing some Bloom filters and writing those to Solr. I'll get to that on the read path. But the main thing here, the Parquet files are much smaller. I think we end up getting about 90% compression, like it's 90% less data in S3 than it was in Cassandra. Part of that is because S3 already has the redundancy built in, so we don't need 3 AZs the way we did with Cassandra. And part of it is because Parquet has run length encoding. It's a columnar data store. You can throw LZ4 or some other compression algorithm on top of it. You get really good compression. So now I want to talk about the read path. This is kind of where the magic happens on those Bloom filters. So if it's very recent data, if somebody's asking us for something for the last hour, or if they're doing a time range, a very large time range that includes the last hour, we're still asking Cassandra and Solr for that time range. But lifting a whole, like tens of millions of files from S3, you could do it, but you'd rather not, right? You want to only lift the files that have the answers that you're looking for. So just like Andre mentioned that Cassandra uses Bloom filters to decide, might this data be in this SS table? And the nice property of a Bloom filter is if it says no, it's definitely not. If it says yes, then it's adjustable, but let's say it's like 99% probability that it's yes. So this means that if we have, if our Bloom filters say lift these 1,000 files out of S3, then 990 of them include the answers that we're looking for, and we lifted whatever that was, I can't do math on stage, 10 files that we didn't need to. But the other key here is it's highly parallel. So we're able to, and again, we've decoupled state from compute, and so we're able to scale if we want to be able to scale, if we want to be able to scale our reads, we can just add more nodes to the Spark cluster. They read more objects in parallel. So to recap the lessons we learned, overall Kafka is really valuable part of our platform, works great on EBS. I'm not sure if we ever ran it on ephemeral, but yeah, definitely use EBS for it. But if you're expecting massive scale, keep in mind the cross-AZ replication costs. For example, 2 gigabytes per second for 1 month adds up to 5 petabytes. Also keep in mind that a single broker causes availability problems, not data loss, but temporary glitches. Small clusters are easy to operate. Larger clusters have more issues. So that's, again, just like I was saying with Cassandra, if you can operate more smaller clusters rather than one huge cluster, you'd really prefer to do it. For Cassandra, the main thing we learned is that Cassandra and EBS have both come a long way in a short time. When we started, we actually were running just pure Cassandra on magnetic EBS, and it fell over instantly. This was back in 2013, 2014. And in fact, DataStax's advice still on their blog today from 2014. Unless you want to add more complexity for your operations team, use ephemeral. Today, the same blog, but more recent post says GP2 is the best choice for most workloads. So make sure you check the date on blogs that you're reading about, particularly about Cassandra or EBS. Something else to keep in mind for Cassandra, on the one hand, it's really good at handling bursts, which is normally a good thing. But when you're benchmarking a database, if you're benchmarking MySQL or Postgres, you could just ram data into it, and if it's not accepting the inserts, then it's not working. If it's accepting the inserts, it's keeping up. Good enough. With Cassandra, it will accept bursts And the way that that data burst ends up impacting it is it puts off the compactions, those SS tables that it's writing to disk. It wants to compact those into fewer, larger SS tables. But if it's not keeping up, it can just wait to do that a little bit. What this means from a benchmarking perspective is you want to run longer benchmarks. Watch for pending compactions, watch for block native transport requests while you're running those, and also make sure that you match your benchmark. I mean, this seems obvious, but people will target like, oh, I want to do 1 million writes per second, and so they do 1 million writes per second, and bam, done. But if you're also doing 100,000 reads per second, or even 1,000 reads per second, that can significantly affect things. There's a tool called Cassandra Stress, which amazingly enough does all of this. You can tune your object sizes, your read-write ratios, your key distribution, so you can use that single tool to match what you think your production workload is going to be. For Amazon EBS and S3, the main thing we learned here is that higher latency doesn't always mean lower throughput. For some of you, your workload may be all about time to first byte. And in that case, if you need that first byte in under a millisecond, today you're not going to get it from S3. Probably not going to get it from EBS either. You're going to need it in memory. But for massive workloads, when you're lifting tremendous amounts of data and you need it in, say, a second, you can still do that with S3. It can be just as fast as ephemeral. The key there is that just as we've seen CPU megahertz kind of top out and we've just started throwing more cores at problems, you can bypass the high cost of really fast storage by increasing parallelism to slightly slower storage. And also being able to decouple compute from state leads to all the same wins that stateless services brought to web front ends and the like. It's really, that's been one that we didn't anticipate going in, but we've learned a lot, and that's been tremendously helpful. One last thing, we have really high write rate to S3, and this is something that we struggled with initially, and there's some blog posts out there, but we didn't find them super clear, so I wanted to put this out explicitly. Just like Cassandra has sort of a ring structure, and you want to avoid hotspotting by writing all your data in one place in the ring, S3 likewise could be viewed as a ring structure. And the objects, unlike Cassandra, they're not hashed. They appear around the ring in lexicographic order. What that means is that all the object names that you wanted to use, like, we'll start with date, we'll start with customer ID or something like that, we'll tend to hotspot. Adding some randomness and 5 bytes for us has been way more than sufficient, talking to the S3 team. Adding sufficient randomness at the beginning of the object name will completely alleviate that problem. We've had over 1 billion objects and 5 petabytes in a bucket. That's by far not the biggest bucket in US West 2, for instance. And that was our production bucket. And while it was taking regular production workload, we had an additional workload that we needed to run against it. It was 1,600 API calls per second for 2 weeks straight, and it didn't have any impact. I don't think that would have been the case had we not arranged the data well to begin with. I'm going to hand the mic back to Gene, or do we want to just come all on stage and do questions? Yeah, let's all come up.
So basically, that's kind of a walkthrough of how we handled some of these really large data problems. So really high throughput, a lot of data in motion, a lot of data at rest, but because of our retrospective analysis, data at rest from a year ago is just as relevant as data from this afternoon. So how do you build a system like this? The first version of our product was pretty expensive. We were struggling with data sets that could not fit in RAM, as we mentioned, so it's all SSD backed. And then we were able to find a way to get this data organized in Parquet and S3. We had a 95% cost reduction. We actually have a viable business on top of a ludicrous amount of data. So at this point, I really want to leave you guys with this session with the sense that really aggressive workloads are really manageable if you just embrace the basics of AWS. get passionate about storage, get passionate about like EBS and throughput, IOPS, get passionate about S3. S3 is the oldest thing out there, and it is, in my personal opinion, the coolest piece of technology in all of AWS, and they hate it when I say that. But it is, we have gotten 1/4 terabit a second out of that thing. I mean, where do you get that, right? So what can you do with that if that becomes all of a sudden easy? So with that in mind, questions, there's 2 microphones. We can't see you really well because of these lights.
I can see a hand up, but...
But go up to the microphone, please, so if you have questions.
In one of your Cassandra slides, you mentioned to not use vnodes. Can you?
Oh,
Good one.
I knew that I was going to miss some of my speaker notes. So if you're using regular Cassandra and not DSE search, I definitely use vnodes. It makes operations way easier. However, if you're using DSE search, you don't want to use vnodes. The Solr query ends up being expanded into, like, if you have 32 vnodes, then the coordinator breaks that query up, sends it to each node that needs to answer the question, and each of those queries on each of those nodes has 32 OR clauses added to it by the coordinator because of the vnodes. So that's not great.
Did you look at using Kinesis instead of Kafka, and if so, what made you?
Yeah, so in the early days, like one of the things that we expected, like, 3 or 4 years ago, was that we might need to be on-prem with customers that had their own data centers. Customers that are security sensitive were concerned about that. That's less, the landscape's changed really fast. That's less of a concern now, but at the time the goal was to not be too married to AWS. Today, one of the things, I don't think that Kinesis allows fan out. I'm not sure if you can have 2 consumers consume the same stream from Kinesis. Anybody know? If it doesn't, I would wait till it does, because that being able to test in production has been a huge, huge win for us.
Thank you.
Yeah.
Along similar lines, have you considered like SNS and SQS in sort of as a fan out and guaranteed delivery once?
Yeah, that's one again where, so the data that's in Kafka is in Kafka even after it was consumed for however long your buffer is. So we do like 24 hours. We used SNS and SQS briefly, but one thing that we couldn't do with that was say, hey, we just consumed this data once and we think we got it wrong, who want to reconsume it? It looked to me like it was gone once you'd marked it as consumed. And you certainly couldn't stand up a second copy of your production engine and run it on the last 2 hours worth of traffic without having first known that you wanted to keep a second SQS topic around just in case you wanted to do that.
So how many nodes in your Cassandra cluster, and how big each node?
The largest cluster that we've run was over 250 nodes. I don't remember exactly. I only remember it because of a specific issue we ran into it when we added the 256th node. Today we tend to target a smaller. We're at, like, I think the most recent hot shard was 180 nodes. So that was the first part of your question. What was the second part?
How big each node?
Oh, so those are i2 2XLs. So it's 1.5 terabytes of SSD. We have about 500 gigs of Cassandra data and 500 gigs of Solr indexes per node.
Okay.
On that. Yep, and have we?
So, really great talk. Thank you for all the in-depth technical details. Now that you have this really impressive basis, what's next? Basically, 2 questions specifically. One, now you have one data source. At least one of the earlier slides, you showed packets from on-prem customer systems.
Right.
Have you thought about getting data from the cloud? Users in the cloud somehow getting cloud packets in?
Yeah, we are already. Yeah, that's or has the I don't know if the embargo is lifted on the
network company.
Yeah.
Yeah, so I think the embargo officially lifted like within the last several minutes. They had an email that said we can talk about this now at the end of the talk, not on the front part of the talk. Kind of funny, but yeah, we are now AWS network security competency certified. So we're kind of a launch partner on that front. But honestly, the idea is that this is pretty available. It's pretty approachable. Everybody should be doing it.
Yeah, and the cloud is definitely like people that are in the cloud is definitely one of the groups that we're targeting. This was never envisioned as being a strictly on-prem. It was, data centers, offices, ICS environments, the cloud, anybody's cloud.
To be honest with you, the industrial environments, they're super cool. You get to see some really crazy stuff there. It's like going back to the 1990s and discovering malware for the first time. It's like, wow. There's botnets that are out there that are being beaconed to. They haven't existed in 20 years, but some piece of Windows 95 oscilloscope somewhere is beaconing out to...
I think we'll take the other ones.
By the way, there's probably going to be a secondary market. I'm collecting all that stuff.
Yeah. Okay, I know we got a couple more questions. I think we're going to drop down here so that the next speakers and stuff can come in and start setting up. Thank you, guys.